Welcome to a special edition of ChemVid. I'm going to be finishing the thermochemistry notes, number 3, number 4, and number 5. So if we went too fast in class, or if you just need some extra help, this video can help you out with how we use Q equals MC delta T to calculate delta H. Alright, so let's start off with number 3. In this, they give us some vital information, so let's pick it out. You conducted a calorimetry experiment. When you see calorimetry, that should make you think of Q equals MC delta T. We always use this equation whenever we do anything with calorimetry. So that should be like a tip-off to you. Okay, so we conducted an experiment in class, and you found out that 5 grams of NaOH caused the temperature of my solution to change 15 degrees. The total mass of my solution was 100 grams. If the specific heat of the solution is 3.34, how many kilojoules of heat was let off? Okay, so from what I gather, it seems like they give me the information that I need for Q equals MC delta T for the solution. Okay, so I'm going to go down here, and it seems like I have the mass of the solution, the specific heat of the solution, the change in temperature of the solution, so therefore I can calculate the heat of my solution. So I'm going to organize my work. 100 grams is the mass. 3.34 joules per grams degrees Celsius is the specific heat, and the change in temperature was 15 degrees Celsius. Now, knowing my equation, I'm going to take my mass times my specific heat times my change in temperature, and I get a heat of 5,010 joules. But if I look back at my equation, they didn't ask me for my heat in joules, they asked it for kilojoules. So I'm just going to do a quick conversion. 5010 joules. Sorry, for some reason my pen froze. There we go. 1,000 joules is equal to 1 kilojoule. So this equals 5.01 kilojoules. So in order to answer the first question, I needed to use Q equals MC delta T, and I needed to do a short conversion. Oh, sorry, I totally scratched that out. There we go. All right, and I had to do a short conversion. Now, as far as sig figs go, I look at my numbers that I measured. So I measured the temperature, and I measured the mass, and it looks like the mass has 1 sig fig right here. So therefore, my answer, my final answer, will be 5 kilojoules of energy. And that answers the first question. Now, the second part asks, what is the heat, or the delta H, of my solution? Now, the thing about delta H is that's the heat content of a system, and it always has the same units. Delta H is always written with kilojoules per mole. So delta H's units become my equation that I need to know. I just found out that 5 kilojoules of energy was released when sodium hydroxide was dropped into water to create a solution. So I know that 5 kilojoules goes on top. Now the tricky part is, what is the moles? Well, the moles is anything that caused a temperature change. Okay? So in this case, when I go back through, I created a solution by dropping sodium hydroxide in water. Well, my water didn't do anything, it didn't break apart. But I know that sodium hydroxide breaks apart into sodium ions and hydroxide ions, and that uses energy. So therefore, I am going to take my 5 grams of sodium hydroxide, because that's the thing that caused the temperature change, and I'm going to convert it into moles. Alright, so after I recognize that, 5 grams of sodium hydroxide, I go from grams of sodium hydroxide to moles. There are 40 grams. I got that off of the periodic table. And I get 0.125 moles of sodium hydroxide. And I know that when 0.125 moles of sodium hydroxide break apart, it releases 5 kilojoules of energy. So my delta H is equal to 5 kilojoules of energy divided by 0.125 moles of sodium hydroxide. And I plug that in, and with sig figs, I get 40 kilojoules per mole when trying to dissolve or when creating a solution of sodium hydroxide. So the important things in this problem that I'd like you to recognize are calorimetry always deals with Q equals MC delta T, no matter what. Okay, calorimetry, that's what we do. By using Q equals MC delta T, we can thereby calculate the heat given off in a reaction, in a solution, in whatever transfer we have. Then, I'm able to calculate the enthalpy by doing a simple mathematical division. Kilojoules divided by moles, and I get 40 kilojoules per mole. So the heat of the solution is 40 kilojoules per mole. Now, this is it. What if they had asked me, let's use green. What if they had asked me, instead of the delta H of my solution, what is the delta H of my reaction? Well, I know that in a system, you have your system and you have your surroundings. In this case, the sodium hydroxide was the thing that broke apart. That's my system. And the water was my surroundings. So whatever energy my sodium hydroxide gave off, my surroundings, or my water, the solution, had to absorb. So I know that this value is exactly the same, 40 kilojoules per mole. However, while my water was absorbing it, which makes it a positive delta H, my sodium hydroxide was releasing it, which makes it negative. So my reaction, or the sodium hydroxide, is a negative 40 instead of a positive. All heat is connected this way. When heat is absorbed, that same amount of heat has to be released, and vice versa. So therefore, the only thing that changes when somebody asks you about a solution versus a reaction, or a system versus the surroundings, is just the sign. One is negative and one is positive. Alright, now on to number 4. So in this one, they say write the balanced chemical equation for the combustion of 2 moles of acetylene. So here's my acetylene, so I'm going to write out C2H2. I know combustion reacts with oxygen, and I know it always produces CO2 plus H2O. Now in this, they actually give you a hint. It says that I need 2 moles of acetylene. So what that means is, I know that I have to have a 2 in front of acetylene, 2 moles. So now I can balance it just like normal. 2 times 2 is 4, so I would need a 4 here for the carbon. 2 times 2 is 4 for the hydrogen, so that means I need a 2 here. 2 oxygens here, 8 oxygens here, that's 10, so I need a 5 here. So I did the first part of the question, balancing the chemical equation. Now it asks me to calculate the heat released when 9 grams of oxygen react with excess acetylene. Because it says excess, I know that my limiting reactant is oxygen. So I can just start off with 9 grams of oxygen. But instead of asking me to go into another component, or how much carbon dioxide will be formed if I use 9 grams of oxygen, what it's asking me for is the heat. So I want to look, and my delta H tells me how many kilojoules there are per mole. So the first thing I want to do is I want to go from grams of oxygen to moles of oxygen. Then, once I'm in moles, I can go directly from moles of oxygen to kilojoules because I have the relationship right here. Negative 726.5 kilojoules is equal to 1 mole. Alright, so now that I know that, I can do what I usually do. 36 grams, I get this off the periodic table, that's equal to 1 mole. I look at my balanced chemical equation, and in the reaction, it says that for this reaction, I have this many kilojoules per mole. So in this reaction, I have 5 moles of oxygen and negative 726.5 kilojoules comes off in this reaction. I can plug that in, and I get 36.3 kilojoules of heat. So the thing that I want to point out in this question is enthalpy, or delta H, is a conversion factor. It tells you how many kilojoules there are per mole of a substance. So I can use it in dimensional analysis in order to find out how much heat was released. Second thing I want to point out is that you need the balanced chemical equation because while it gives me the delta H for the reaction, in the reaction I can have more than 1 mole of one component. So I always have to be careful of that. Okay? Alright, let's move to the next one. Alright, last example. You did one of these, I did one of these in the other video, but let's go over it. So this one is asking me if I have 328 grams of acetic acid and it condenses from a liquid, or it condenses to a liquid. So this is saying I'm going from a gas to a liquid. Okay? Up here I have fusion. Fusion is when I go from a liquid to a solid. And I have vaporization. Vaporization is when I go from a liquid to a gas. So since I want to go from a gas to a liquid, I will be using the delta H of vaporization. However, since my delta H is positive when it goes from a liquid to a gas, when I do the opposite, when I go from a gas to a liquid, the delta H backwards needs to be a negative 23.4 kilojoules per mole. Okay? So whenever you're doing a phase change, it's always the same number, but you need to make sure that you have the correct positive or negative sign. Alright, now, like I said in the last section, this is a conversion factor. So now all I have to do is go from grams of acetic acid to moles of acetic acid using the periodic table. And then I can go directly from moles to kilojoules using my delta H. So 1 mole is equal to negative 23.4 kilojoules. 1 mole is equal to whatever I calculate off of the periodic table. And so all I have to do is calculate that out, and I have how much energy it takes to condense a liquid, condense a gaseous acetic acid to a liquid acetic acid. Okay, so that covers the main topics that the thermochemistry notes went over. If you're still having difficulties, feel free to come and see me so we could go over this together, but I hope this helped. Have a good day.